Welcome to Aviation World.
Welcome to this presentation covering the pneumatic system on the A320 series aircraft. This highly automated system supplies high-pressure bleed air for air conditioning, wing anti-icing, engine starting, hydraulic reservoir pressurization, and water pressurization. We will begin this lesson by looking at the sources of pneumatic air.
High-pressure air can be supplied from three sources: engine bleed, Apu bleed, external high pressure, HP, ground connection. We'll look at the engine bleed source first.
In flight, the primary sources from pneumatic air are the engines. The two engines' bleed systems are the same. Air is bled from two engine compressor stages, the intermediate or IP stage and the high pressure or HP stage. The IP stage is the primary source of air during flight. The HP stage is used only when there is insufficient pressure from the IP stage. This is normally the case when the engines are at idle during ground operations or during long idle thrust descents. When HP stage air is in use, a check valve prevents this high pressure air from entering the IP stage. A high pressure valve is installed that can cut off bleed air.
Once engine speed is high enough, and IP air pressure is sufficient, the HP valve closes automatically. IP and HP air are never used at the same time. The air from either the IP or HP stage then goes to a common engine bleed valve, which acts as a shut-off and pressure regulating device. The engine bleed valve can operate automatically or be manually controlled from the cockpit. Since the temperature of the bleed air is high, it passes through a pre-cooler before being distributed to various users. The pre-cooler uses cool air from the engine fan section to regulate the temperature.
An overpressure valve, located just upstream of the pre-cooler, prevents abnormally high pressure air from reaching the system. The Engine 1 and Engine 2 systems are exactly the same. A cross-bleed duct connects the two.
A cross-bleed valve permits their interconnection or isolation. The cross-bleed valve operation is normally automatic. The valve can also be controlled manually if necessary.
The APU can also be used for bleed air supply. The APU is normally used as a bleed source on the ground for air conditioning and for engine start. APU bleed air is also available in flight. Limitations prohibit the use of APU bleed air above 20,000 feet. APU bleed air is controlled using the APU bleed valve. This valve is normally controlled by the crew but can operate automatically when necessary. The APU provides pneumatic air to the system via the cross-bleed duct and is connected to that duct on the left side of the cross-bleed valve.
A unique feature of the system design is that it gives priority to the APU as a pneumatic source. This feature reduces crew workload during engine starts.
When the crew selects the APU as a bleed source, the APU bleed valve opens. It immediately supplies the left side of the system. This also causes the cross-bleed valve to open automatically, allowing the APU to provide bleed air to both sides of the system. If the engines were running, the engine bleed valves would automatically close. APU bleed air has priority over engine bleed air.
External high-pressure air can also be used to supply the pneumatic system. For example, if the APU is inoperative, a high-pressure air cart could be used to provide a source of air to start the engines. This is not to be confused with the low-pressure air discussed in the air conditioning lesson. External high-pressure air is connected in a separate location than the external low-pressure, air-conditioned, air. When either external air source is connected, the aircraft bleed sources must not be used.
The pneumatic system is controlled and monitored by two bleed monitoring computers, or BMCs. There is one BMC for each engine bleed system.
BMC1 is also responsible for the APU bleed system. The BMCs are interconnected, and if one fails, the other takes over many of its functions.
There are leak detection loops installed in the vicinity of the APU or fuselage ducting, engine pylon ducting, and wing ducting. If a leak is detected, a signal is sent to the BMCs, which in most cases will automatically isolate the affected area and alert the pilots via the ECAM. A leak detection loop along the hot air duct in the engine 1 pylon and the duct for the APU bleed air is monitored by BMC1. A leak detection loop along the hot air duct in the engine 2 pylon is monitored by BMC2.
Dual leak detection loops are provided for hot air ducts in the wings and that portion of the fuselage ducting forward of the APU bleed valve. One loop is monitored by BMC1, the other loop is monitored by BMC2. In these areas, both loops must detect a heat rise before an alert is generated or automatic action is taken by the BMCs to isolate the leak. If one of the loops fails, the BMCs will act if a bleed leak is detected by the remaining loop. That concludes the section. Now it's on to controls and indicators.
We will look at the ECAM bleed page first, and then the pneumatic system controls located on the air conditioning control panel. The lower half of the ECAM bleed page is dedicated to the pneumatic system.
The two engine bleed sources are located at the bottom of the page. The IP and HP sources are represented with labels that are always displayed in white. The automatically controlled HP valves are normally displayed in green. In this example, the HP valves are fully closed.
In this example, the HP valves are open. HP air is in use, replacing IP air. The check valves which prevent HP air from entering the IP duct are not displayed on the bleed page.
Finally, in this example, the engine 1 HP valve is closed and it should not be. It is being commanded to the open position by the BMC, but it is not responding. The engine bleed valves are normally displayed in green. In this example, the engine bleed valves are open normally. In this example, the engine bleed valves are closed normally. This can be accomplished either automatically or manually by the crew. If the engine bleed valves are open or closed in disagreement with their commanded position, they are displayed in amber. This valve is often misidentified as the IP check valve because of its proximity on the page to the IP icon. It is not the IP check valve. It is the bleed valve through which either IP or HP air can pass.
The engine numbers are amber if the associated engine, N2, is below idle. Basically, they are amber if the engine is not running. They change to white if the engine is running at idle speed or above.
The performance of the overpressure valves, which are not displayed on the bleed page, can be monitored using the digital pressure readouts. They are normally green and change to amber if the pressure is abnormally high or abnormally low. The performance of the pre-coolers, also not displayed on the bleed page, can be monitored using the digital readouts of the pre-cooler outlet temperatures. The temperature readouts are also normally green. They change to amber if the temperature exceeds preset thresholds for specific time periods. They also change to amber if the temperature is less than a preset minimum threshold.
The white APU label is always displayed. If the APU master switch is off, the area above the APU label is blank, as shown here.
The APU bleed valve is displayed if the APU master SW is on. In this example, the APU is running but APU bleed has not been selected on, so the APU bleed valve is shown cross-line green. This indicates that the valve is not fully open. This example shows how the APU bleed valve is presented when the valve is fully open.
The valve is displayed cross-line amber if the APU is running and the valve has commanded to open but has failed to do so. The cross-bleed valve can also be displayed in either green or amber. In this example, the cross-bleed valve is closed. The valve would be displayed in amber if valve position disagrees with the commanded position. In this example, the cross-bleed valve is open.
If the valve is in transit, it will be briefly displayed in amber. The Gnd icon is quite simple. It is displayed when the aircraft is on the ground. It is not displayed in flight. It does not indicate whether or not high-pressure air is connected to the aircraft. It only indicates that high-pressure air connects to the left of the cross-bleed valve. The connection of external HP air can be confirmed by observing an increase in pressure. Advance to see the connection of HP air. HP air is now connected and we can see a rise in pressure. The Gnd indication does not change. No indications are provided for the connection of low-pressure conditioned air. Not even a change in pressure or temperature is indicated because the air bypasses the pneumatic and air conditioning systems. Low-pressure air is discussed in more detail in the air conditioning lesson. Do not use engine or APU bleed air in combination with external HP air. The APU and engine bleed valves must remain closed. Now let's move on to the air condominium panel. The air condominium panel is located in the forward center of the overhead panel. Pneumatic controls are located at the bottom of the panel. The ram air PB is not part of the pneumatic system.
Each engine bleed valve can be controlled using the respective engine bleed push button. The push buttons are normally left in the on or lights out position. They are rarely used except in response to abnormal procedures.
Closing the engine bleed valve also causes the HP valve, if in use, to close.
It also shuts down the associated pack. Here you can see all of the possible reasons that the engine bleed valves may close. The fault light in the engine bleed push button illuminates if the BMC closes the engine bleed valve for a bleed leak, an overtemperature, or an overpressure. The bleed valve can automatically close to isolate the duct that is leaking.
It also illuminates if the valve remains open when it should be closed. For example, it should close during engine start and when APU bleed is in use.
The APU bleed valve is controlled using the APU bleed push button. If the APU is running, selecting the push button on opens the APU bleed valve. You will see this in action in the normal operation section of this lesson.
The BMC automatically closes the APU bleed valve to isolate a leak detected in the APU duct or in the left side of the system. This causes the fault light in the APU bleed PB to illuminate, accompanied by an ECAM message. The fault light extinguishes when the APU bleed PB is selected off, lights out.
When APU bleed is not in use, the BMC automatically closes the cross bleed valve if the cross bleed knob is in auto.
The X bleed knob allows the crew to override the automatic BMC logic when necessary. In this example, the cross bleed valve is open because the X bleed knob is in the auto position and APU bleed is in use. Advance to move the X bleed knob to the shut position.
The cross bleed valve is now closed, isolating the left side of the system. We'll use the open position later. Well, this completes controls and indicators. Now it's time for normal operations.
You are accomplishing your preliminary cockpit preparations. Normally you would not have the bleed page displayed. To better illustrate what occurs in the pneumatic system, we will keep it in view for academic purposes. All the pneumatic-related PBS on the air condominium panel should be in their normal lights out position, and the X bleed knob should be in its normal auto position. On the bleed page, note that the engines are shut down and the bleed valves closed. Because the APU bleed valve is displayed, you know that the APU master switch is on. APU bleed air, however, has not yet been selected on.
It's time to select APU bleed air on. Remember, do not use APU bleed air if ground air is connected. Advance to select APU bleed air on. The APU bleed valve opens and the left side bleed pressure and temperature change to green when they reach the normal operating range. The fault light and the Pack 1 push button extinguishes. Advance to see the cross bleed valve open automatically and the APU supply the right side of the system. After a few seconds, the cross bleed valve opens automatically. The temperature and pressure on the right side are now in the normal range and Pack 2 is operating. The Pack 2 fault light has extinguished. The pressure displayed on the bleed page is also displayed on the engine page, which would normally be in view during the engine start. You will see those indications in the power plant lesson. We will keep the bleed page displayed during this lesson. Usually APU bleed air is used for engine start. We will move on to that now.
The pack flow control valves close automatically during the start sequence, ensuring all APU bleed air is available for engine starting. Advance to move the N mode selector to IGN/start. Watch the pack flow control valves close. Engine 2 is now running. The engine number has changed from amber to white. Its bleed valve remains closed throughout the start sequence and will remain closed because APU bleed air is in use. The pack flow control valves open automatically approximately 30 seconds after the start sequence is complete.
It's now time to turn off APU bleed air in preparation for shutting down the APU. Advance to select the APU bleed push button off.
The APU bleed valve closes, the cross bleed valve closes, and the engine bleed valves open. This all occurs automatically.
The APU bleed valve is removed from the bleed page. Since APU bleed was used, the APU will continue to run for up to 2 minutes to provide for a cooling period prior to shutdown. The avail light may remain illuminated during the cooling period, depending on the aircraft. When the APU speed drops below 95%, the avail light extinguishes. Assuming no abnormals occur, the pneumatic system configuration will remain as you see here for the remainder of the flight, with one major exception. The BMCs will open and close the HP valves as necessary. If they determine that IP air does not meet the bleed air demand, the HP valves will open. For example, during taxi, the HP valves will most likely be open due to the reduced power setting. We have now moved out to the runway and are ready for takeoff. Advance to simulate applying takeoff thrust.
The BMCs automatically close the HP valves when engine thrust is increased. Advance to simulate liftoff from the runway. In flight, the Gnd icon is removed from the bleed page. We are now in flight and have decided to select wing anti-ice on. The activation of wing anti-ice is displayed on the bleed page. Wing anti-ice is covered in more detail in the ice and rain protection lesson. This completes the section of this lesson. We'll take you back to pre-flight again. Assume that the APU bleed is not operational on today's flight. It will be necessary to use a high-pressure external air cart for engine start. This should be accomplished using the checklist found in your FCOM. Once again, the bleed page is shown throughout this procedure for academic purposes. The availability of bleed air at the engine start valves is indicated on the engine page, which is normally displayed during this procedure. The first thing you will be required to do, before having external air connected, is to manually shut down the packs. This is to eliminate the possibility of the external high-pressure air contaminating the packs. Advance to select both pack PBS off.
We can now have external high-pressure air connected to the aircraft. Advance to simulate connecting high-pressure air.
You now see temperature and pressure in the normal range on the left side of the system. That is the only indication on the bleed page that HP air is connected. Next, you are required to make sure APU bleed is off, which it is, and select the Gnd Bleed PBS off. This ensures the engine bleed valves remain closed during the start. Advance to select both Gnd Bleed PBS off.
Since we will be starting engine 2 first, the next step is critical. We are now required to open the cross bleed valve to allow external air to reach the number 2 engine. Advance to move the cross bleed knob to the open position. The cross bleed valve is now open and HP air is available to start engine 2. Notice the temperature and pressure indications on the right side of the system. We can now proceed with a normal engine start. This would normally be followed by a cross bleed start of engine 1. After engine 2 is started, we would leave the cross bleed valve open to use bleed air from engine 2 to start engine 1. Following your checklist, cleanup items would include selecting both engine bleed push buttons on, moving the cross bleed knob to auto, and selecting both pack push buttons on. You are now in flight and everything is normal. Advance to see what happens if an engine bleed overheat occurs. A single chime and master caution lights alert you to the problem, along with fault lights on the air conditioning panel. The bleed page is displayed automatically and indicates that the engine 1 bleed valve is closed. The BMC closed the valve in response to the overheat. This also caused pack 1 to shut down.
The ECAM directs you to close the engine 1 bleed. Advance to select the English 1 bleed PB off. With the English 1 bleed PB selected off, the fault light becomes a monitoring light. The fault light will extinguish when the overheat condition no longer exists. Advance to move the X bleed knob to open.
Now engine 2 bleed is supplying air to both packs. The output of a single engine bleed is capable of supplying both packs. On the next screen, we will see what this same abnormal looks like if you were using wing anti-ice when it occurred. Here is the bleed overheat again. Engine 1 bleed is already selected off. An additional action step is displayed prompting you to select pack 1 off prior to opening the cross bleed valve. This is because the bleed output of one engine is not capable of supplying both packs and wing anti-ice simultaneously. Advance to select pack 1 off. Selecting the pack off allows you to retain wing anti-ice. Advance to move the cross bleed knob to the open position.
Both wings are now provided with anti-ice capability.
Once you have cleared to the status page, you will be reminded that wing anti-ice, depicted as WAI, and 2 packs cannot be operated at the same time when you have only one engine bleed. You would now clear the status page and consult your FCOM for additional information. Note: the use of APU bleed air as a supplement is not an option. Remember, if APU bleed air is on, the engine bleed valves close automatically.
We will now contrast the previous abnormal, bleed overheat, with the detection of an engine bleed leak. Here again the engine 1 bleed valve has been closed automatically by the BMC. This results in the loss of pack 1 and left wing anti-ice. Unlike the previous abnormal, opening the cross bleed is not an option. You do not want to feed the leak using engine 2 bleed. You are directed to select wing anti-ice off since it is more dangerous to operate with wing anti-ice on one wing than it is to operate with no wing anti-ice at all. Bottom line, You will be operating on one pack and should avoid icing conditions if at all possible for the rest of the flight. You will be confronted with the same result if a wing bleed leak is detected. You will lose bleed capability on the side of the system that experiences the leak. Isolation of the leak, engine or wing, takes priority. When you clear to the status page, you will be reminded to avoid icing conditions. Wing anti-ice and the affected side's engine bleed and pack are all inoperative systems. In the unlikely event that the automation does not work and the appropriate engine bleed valve does not close, or for some reason the cross bleed valve had been manually opened, the BMCs will recognize these situations. The ECAM will direct you to take the proper response. In this example, an engine 1 bleed leak is detected but the engine 1 bleed valve did not close as commanded by the BMCs. We happen to have had the cross bleed valve open when the leak occurred. Notice the extra action steps provided to guide you in taking the additional steps necessary to isolate the leak. Here are some other ECAM messages you could encounter related to the pneumatic system. This first one alerts you that one, or both, of the HP valves is not functioning. Expect low pneumatic pressure when the engines are at idle. Both detection loops on the left wing would need to fail for this to happen. BMC detection of leaks is no longer available on the left wing. This final example is the ECAM message you would see if both BMCs fail. All monitoring and automation is lost. You still retain the ability to manually open and close engine bleed valves, the Apu bleed valve, and the cross bleed valve. You will only notice minor differences in the bleed page. You might notice that the Gnd icon is white on some aircraft and green on others. This is irrelevant because it only indicates the location where high pressure air enters the system. The Gnd icon never indicates if air is connected, regardless of color.